this is a bit of a tester for us to see how it works, but hopefully we might be able to get some teaching done, and just like I was in the classroom, as annoying as ever, I guess. So you'll have to bear with me as I go through this, but hopefully if this works now, we can do our daily videos, or when you don't have a class. What I will do is I'll talk through a couple of exercises, show you the ways that you need to do, and then set you the work. I'm also going to, we're going to look at today integration. I've got the A-level notes, so what I plan on doing is I'm going to attach, like we would normally do in the classroom, I'm going to attach to the assignments on Microsoft Teams the notes for integration. And then these questions, these examples that I'm going through here, are the examples that are in the notes, so that you can follow and fill in the notes as you're going along. And then I'll try and specifically talk about the exercises that you need to be looking at for this particular chapter. So today we're going to have a look at, as it says here, integration. Now we did have to do some work on differentiation, albeit only a small amount was required. We've done more than enough work on differentiation to allow us to continue with this work on integration, because integration is basically the reverse of differentiation. Now, as with any new topic, there's notation that we'll need to discuss. Remember, when we differentiated, we had two types of notation. We could either have something like this, where you've got y equals 2x squared plus 3x minus 5, say, I've just made that one up. Or we could, instead of having y equals this quadratic expression here, I could have f of x equals 2x squared plus 3x minus 5. And then depending upon whether we're using this notation, y equals, or whether we use f of x equals, our function of x is equal to 2x squared plus 3x minus 5, that depends on what we write when we differentiate. So for example, if I was to differentiate this top one here, I would start by writing dy by dx equals, and then remember we differentiate term by term. Just remember the rules when we differentiate. We bring the power down. If there's a number in front, we multiply it. If there isn't a number in front, we just put it there. And then we take one off the power. So if I did this one, 2x squared, bring the 2 down, multiply by the 2, we get 4. And then if I take one off the power, it becomes 4x. The 3x, well, that just becomes plus 3. And then the other point to note is the minus 5, or any constant there, any number on its own without an x attached, just disappears. That's because we could write an x there and it would be an x to the power 0, but if I brought 0 down and multiplied by the minus 5, the whole thing would disappear. Now we never write this x to the 0 in there, so we just know that any constant like that, any number on its own, would disappear. But that's important when we come to integrate and we're doing the reverse of differentiation. What I mean by that is we're going to start here and we're going to go back to here. We're going to have a look at what the function or the curve or the polynomial is. So we're going to go backwards. But that's important to know, because that was minus 5 that disappeared here. But that could have been any number. Plus 7, that wouldn't be there either. Minus 29 wouldn't be there. So any number on its own will have disappeared. We'll talk about that more in a minute. If it was of this, if we use this notation, f of x equals 2x squared plus 3x minus 5, then when we differentiate, we still do it term by term, but we use this dash notation. The one dash there indicates we're differentiating the first time. F prime x, or f dash x, equals 4x plus 3. Now remember, when we're differentiating, we're finding this function that tells you the gradient at any point on this curve. I'll just call it the gradient function. But what we're going to do when we integrate is we go back from this gradient function and we find out what the original function is. Now, as I said before, differentiation, and I've only got a smallish whiteboard to work on, so I'm going to have to, as I go through this, guys, I'm going to have to, you have to bear with me. I'll be rubbing out, but I'll do it as best I can. Now, to undo this, we've just got to think about the process. We've got to undo that process. The idea that if y equals x to the power n, then to differentiate, what we would do, we would write dy by dx equals, and then the n comes down in front, and we take one off the power. So we have n x to the n minus 1. If we want to undo that, so let's say we started with dy by dx equals x to the n, some function of x. Here, dy by dx is 4x plus 3. If we started with that, then to undo that process, well, first off, dy by dx will become y, because we're using that notation. So dy by dx becomes y. And then the n minus 1, we have to undo that by adding 1 to the power. Instead of subtracting 1 from the power, we're going to add 1 to the power. And then we divide by the new power. The reason we divide by that new power is because here the number comes down in front. So when you're dealing with it, the 2 comes down in front. And so to get rid of that or undo that, when that x to the 1 becomes an x to the 2, we have to divide by that 2 as well, because it cancels the 2 that was in front. So we're literally just undoing the process that differentiation does. That's what integration is about. It takes a gradient function like I've got here, the examples in your notes, and then it's going to undo the process and take us back to the original function, the original polynomial or curve. But the process is fairly straightforward. All you need to remember to do, guys, you add 1 to the power and you divide by your new power. There's the rules. Add 1 to the power, divide by your new power. So these are the examples in the book. And like we did with differentiation, where we can do it term by term, here we're going to do it term by term using the undo rule, the idea that you add 1 to the power, you divide by your new power. So question A in the notes, dy by dx equals x to the power 4. If I want to integrate that, because we're using the dy by dx notation, I write y equals, and then I add 1 to the power, so it becomes x to the 5, and I divide by my new power, 5. Here, dy by dx is 3x squared. To integrate, we add 1 to the power, so it becomes 3x cubed. And then we divide by our new power, 3. For this one, dy by dx equals 2x to the minus a half. Well, add 1 to the power. Minus a half plus 1, or plus 2 over 2, becomes positive a half. So we get 2x to the positive a half divided by positive a half, your new power. Now I will go back in a minute and I will see which of these we can tidy up. What happens if it's just a number? Well, you've got to think about where that came from. If I differentiate 3x, that becomes 3 on its own. So it makes sense when I'm undoing that, and I integrate 3, do the opposite, I just put an x on it. So any number, you just attach an x. So 4 becomes 4x. And then this bottom one, dy by dx equals, let me just check you can see that, it just, I'm conscious with the camera that I don't want to write something on the bottom that you can't see. We're just going to do this one, even though there's 3 terms, we just do it term by term. So the first one, you add 1 to the power, so it becomes 5x to the 5. And then we divide by my new power 5. I think you can just see that. The 3x, I go plus 3x squared, add 1 to the power, divide by my new power 2. And then finally, this minus 12x to the minus 7. If I add 1 to the power, it becomes minus 6. And I divide by my new power of minus 6. Tidying this up, on the first one, well, there's no need to tidy it up, it's x to the 5 over 5. For this one, the 3's cancel. So we just get x cubed. For this one, for part C, we're dividing by a half. It's 2x to the power of half divided by a half. Well, dividing by a half is the same as multiplying. Dividing by a fraction is the same as multiplying by the fraction flipped. So I'm going to multiply this top by 2. Instead of dividing it by a half, I'm going to multiply it by 2. 2 times the 2x to the half is 4x to the half. Part D is just 4x. That doesn't need simplifying. Now this one's going to be a little bit more challenging just because of space, so I'm just going to put it here at the end. 5x to the 5 over 5. Your 5's cancel, so we just get x to the power 5. That's not very good. X to the power 5. I apologise if I go in front of the board. I'm going to try and go to the side, but obviously with the A level there's a lot more going on a small space here. So if I do step in front, I'll try my best to step back and so you can see it. 3x squared over 2, well that can't be simplified, we just leave it as that. And then finally, this minus 12 divided by minus 6, we can simplify on the last term. Minus divided by a minus is a plus. 12 divided by 6 is 2, and so we get plus 2x to the minus 6. Now, this, you can see here, for the most part, integration is doing what we would expect it to do. We're just undoing the process of what differentiation does. Things to remember. First off, the rule. Add 1 to the power, divide by a new power. That's all you do every time. When I went through these examples, I added 1 to the power, becomes a 5, and is divided by a 5. Here, x squared, I added 1 to the power, it becomes x cubed, and I divided by my new power 3, and so on. But, whilst you're getting used to this, guys, and the idea, because obviously you've got differentiation in your head on 1, which is a new technique, where you bring the power down and then take 1 off the power. Here, you're adding to the power first, and then you're dividing by your new power. It's worth writing it out fully, like I did here. Dividing by a half. Try not to do too many steps at once. It's worth writing it down, getting the rule in your head. Add 1 to the power. Divide by your new power, and then simplify. Now, this process is a process of what we call an indefinite integral. Indefinite, which I'm going to explain now. This is really important because I'm going to introduce what we call the constant of integration. It's just basically a plus c. Now, all you have to do is remember to put it on the end. So on this, when I finished integrating, so I've got y equals now. So I started with my gradient function dy by dx equals x to the 4. I reversed the process of differentiation because differentiation would have took me here. So I reversed the process to get back to my original curve or polynomial. But I add c. Here I integrate, and as soon as I integrate, I add c. Here I integrate, and after I've integrated, I add c. In fact, on the end of all of these, whenever I integrate, I just add this constant of integration, c. Now, what is the constant of integration? Why is it there? Well, I'll tell you why it's there. Look back to this original example. Y equals 2x squared plus 3x minus 5. If I integrate that, if I differentiate that, then this constant here, like we said before, disappears. So when I want to undo that process, when I want to reverse that process, I can deal with this. I can write 4x squared over 2. In fact, I'm going to do that because I think it would be easy to show you. So let me get rid of some of this a minute. Do bear with me, as I say with these videos. It is a bit like being in the classroom, except for I'm working with slightly different parameters on a slightly smaller scale. And any feedback on these videos would be greatly appreciated. If you just want to put it into the chat, at least then I can try as we're going along to improve these. But if I undo this process, so just as I've done here, I'm going to integrate. So if we started with y equals a differentiate, I get this. Let me say I want to integrate. My starting process was dy by dx equals 4x plus 3. Now, my aim when I'm integrating to undo the differentiation is to get back to this. instead of going from my curve to my gradient function, if I reverse it and I start here, I want to get this back. Now doing this term by term, add 1 to the power, divide by a new power, we get 4x squared divided by 2. Notice I'm not simplifying too quickly yet. While you're getting used to this, just get used to writing it down and simplifying next. The 3, well, we just put an x on that one. So you can see how this is working. When we simplify, the 4 and the 2 will simplify to the 2 and we get 2x squared. So we get that term back. Tick. The 3, we just put an x on. Any number, don't forget, like I said before, any number, 4 just becomes 4x. 5 becomes 5x. Minus 7 becomes minus 7x. Here the 3 becomes 3x. And we've got that term. The problem we have is that if you differentiate a number, it disappears. It's not there. So if I started here, I don't know what that number is. That could be anything. I could have put any number in here that would have disappeared and give me this function if it had been 2x squared plus 3x minus 9. I would have still got this because the minus 9 disappears. So I don't know if there is a number there or not. If this is my starting point and I didn't know that was the function I'm looking for, well, I don't know if there's a number there or not. So we have to preempt that. We have to think, well, there could be a number there. And so what I do is I put a plus c in to acknowledge the fact that there could be a number in here. Now, of course, that might not have been there. So it could have just been 2x squared plus 3x and I would have got this out. And so that c could be 0. It might not be there. But all we know at the moment is that there could be a number, a constant, that when we differentiate it becomes 0, it wasn't there. And so we acknowledge that by putting in a plus c. This is why we call it an indefinite integral, because we don't actually know what this plus c is. And in fact, we have here a family of curves, we call it, because we could put any value of c in there and it will give you a different curve that we're looking at. So all you need to remember when you are integrating, let's go through the key points here. When you're integrating, integration is the reverse of differentiation. Instead of starting at your function and then differentiating to get the gradient function, the function that tells you all the gradient of the curve at different points, our starting point is this dy by dx gradient function equals, and we're going back to the original function, the original polynomial curve. So we just remember the rule. You add 1 to the power first, you divide by your new power next. They're the 2 steps. Add 1 to the power, divide by a new power. And then when you've finished integrating, you add c. Now that doesn't matter if I'm integrating one term or if I'm integrating 3, 4, 5 terms, one after the other, term by term. I still add a plus c. But I only need 1. I don't add 1, 2, 3 terms, so I'm going to write plus c, plus c, plus c. I don't need that. I just write plus c at the end. Now, as I said before, this depends upon notation. We might not, oops, sorry, I get the board rubber. We might not get dy by dx equals. We might get f dash x equals. Well, let's have a look. Let's have a look at notation then. I've got some more examples. So this is the next part in your notes. Just bear with me. It was cleaner, the board, when I started. I think I might just need to get some cleaner on it. I'm sort of ad-libbing this now, so as I'm cleaning, I need to have a selection of jokes, I think, guys, so that as I'm doing this bit of cleaning, I can get a joke with you or something like that. Maybe I'll look at doing that. Just let me check this board. Right. So notation is a key part of this, but it's not too difficult. For example, instead of having dy by dx equals, I might have had f dash x equals. And then we could just put our terms in here. I don't know, 3x to the power 5 plus 4x minus 7. If that was the case, then when I when I integrate f dash x, then what I would get back is f of x. So here f of x equals, add 1 to the power divided by a new power, so you get 3x to the 6 divided by 6. Here, add 1 to your power, 4x squared divided by a new power, 2. The minus 7 just becomes minus 7, and we put an x on the end. And then we just remember to add c. It's as simple as that. We put plus c in just in case there is a constant of integration. In case there is a number that when we differentiated disappeared. And then we just simplify, as we've done before, 3 over 6. Well, the 3 and the 6 gives me a 2 and a 1. If I simplify it, 3 goes into 3 once and 6 twice. So we end up with x to the 6 over 2. Here the 4 and the 2 cancel, and we get 2x squared. Just be careful, it's a 2 on the top this time, 1 on the bottom. The minus 7x is just minus 7x, and the plus c just tags along on the end. So if you're given dy by dx, then your notation will be y equals, I should have put that on there, I'll put that in now, y equals. And if your notation is f dash x as our starting point, then when we integrate we get f of x, we get the original function back. Now there is other notation that we use when we're integrating. Obviously when we're differentiating, our key notation dy by dx, dy over dx, or f dash x, f prime x, they're the two primary notation that you're going to be using. The integration, we have something like this. We have an elongated s, like this. This just means, it's telling you to integrate. And then you would put your function in here, so it could be something like this, x to the 4 plus 7x. And then finally, we have dx. Now, the elongated s just tells you to integrate, so you know that you're going to be integrating if you see that. The dx here tells you what letter you are integrating with respect to. What that means is, I'm integrating x to the 4 plus 7x with respect to x. Now, at the moment, this won't mean too much for you, but I could put any letters in here. I could put v to the 4 plus 7v, as you'll see with a couple of examples, dv. So it's the v's that I want to integrate. Here, this dx bit that we put on the end is just telling me what letter I am integrating. And this elongated s tells me that I am integrating. That's kind of the key bit. So if I got this, the integral of x to the 4 plus 7x dx, well that just becomes x to the 5 divided by 5, term by term, add 1 to the power, divide by a new power, and then this 7x becomes 7x squared divided by 2, add 1 to the power, divide by my new power, and then don't forget to add a plus c. Right, the next part of your notes, sorry, here we are again, I will get this right, I think it just needs a cleaning fluid on it. The next part of your notes uses that notation. The next part of your note uses that notation. So let's go through them examples again. As you're watching this video, I don't know if you can print off the notes, that would be ideal. If you can't print off the notes, at least you can make a note of this, and at some point, when we get back to normal, you'll be able to fill in the notes and maybe re-look at the video. If I just leave these videos on Microsoft Teams, then you can look back and you can fill in the notes as we're going along. But I just think this is the easiest way to go about it. So, part A, we've got the integral of x to the minus a third plus 2x cubed dx. Now don't forget, if you see this in the book, this elongated s tells me I'm integrating. These are the two terms I'm integrating. Dx just tells me it's the x terms that I'm integrating. So I'm going to apply my rule. Add 1 to the power, divide by my new power. So this becomes, if I add 1 to minus a third, or if I add 3 over 3, then I get x to the 2/3. And then I'm going to divide by 2/3. Notice I am not simplifying at this stage. Next term, 2x cubed, add 1 to the power, so it's a positive 2x and it becomes a 4. And I divide by my new power 4. And then I add a c. At this point I can simplify. Dividing by a fraction is the same as timesing by a fraction flipped. We're dividing by 2/3, so that's the same as multiplying by 3 over 2. So we get 3 over 2 x to the 2/3. 2 over 4. Well, the 2 and the 4 cancels, and we get x to the 4 over 2. And then we add c. Part B. You've got the integral of t to the minus 2 plus 6t to the 3/4 dt. Now notice the notation. Here, instead of using x's, I've used t's. So it's not dx we have here, it's dt. All that's saying to me is I'm integrating these two terms here, which have t's, with respect to t. T's the letter that I'm integrating this time. It's just notation. So let's just do it term by term. Add 1 to the power, t to the minus 1, and I divide by my new power, minus 1. I am not simplifying yet, I will simplify next. Here I add 1 to the power, 3/4 plus 1. I'll do it as an aside, 3/4 plus 1. Well, that plus 1 is the same as 4 over 4. All I do is, I have a look here, it's 4 on the bottom, so I write my plus 1 as 4 over 4. And then when I add that, I can see I've got 7 over 4. So I'm going to do plus 6t to the 7 over 4. I've added 1 to the power. I divide by my new power of 7 over 4. Once we've done that, then I simplify. So I'm going to term by term have a look. Actually, before I do that, as I said to you before, I've done the two terms. Just put in a plus c. Get in the habit, when you integrate, of just adding c on the end. First term here, divided by minus 1, t to the minus 1 divided by minus 1, is just minus, I'm just going to put the minus at the front, t to the minus 1. This term, dividing by 7 over 4, is the same as timesing by 4 over 7. Now, there is that 6 at the front. So I'm going to do 4 over 7 times the 6. Again, I'll do a little side here, but 4 over 7 times by 6, because we're not dividing by 7 over 4, we're timesing by the fraction flipped. Well, when you're multiplying these together, because 6 is like 6 over 1, you just do 4 times 6 is 24 over 7. So we get plus 24 t to the 7 over 4 over 7. And that plus c just tags along. We just need to get in the habit of writing that plus c down. Question C in the notes. You've got the integral of 2v squared minus 1 all over v squared dv. Look at the notation. Our letters here now are v's, and so we're integrating these terms with respect to v. That's all it's saying. Most of the time it's just going to be like this with x's, but I think you can see, if we use just different letters, what I'm trying to say there with this dt, dv, dx, what it's doing. It's just telling you which letters that we're integrating. Now, like with differentiation, we're going to do it term by term as we have been doing. Add 1 to the power, divide by a new power. But we may have to manipulate it a little bit, because this is all over v squared. What I can do before I actually go on and integrate is get this in a position where I'm ready to integrate. So this is the same as, I'm going to write these two terms separately over that common denominator of v squared. I'll just write it in, and there's my dv. So at the moment I'm not integrated, I'm just playing around with this bit inside so that it's in the right format to allow me to integrate. You can see here, if I've got two things over a common denominator of v squared, then I can write them both over my common denominator. But in the same way, I can go backwards. We've done rules of indices at the beginning, so hopefully this should be fairly clear. And then the v squareds cancel here, so what we actually get is the integral of 2. That term just becomes 2 because the v squared will just cancel like that. This one, we don't want the v on the bottom, so I'm going to take it to the top as a minus power. So it becomes minus, the minus just stays there, and that becomes v to the minus 2 dv. So I've had to do a couple of steps. I still haven't integrated, so my integral sign there, this elongated s, is still there. My dv is still there. It's only when I've actually integrated will they disappear. And I've had to manipulate it so that I've got two terms that I can now integrate like I would do before. Now I'm ready to go. The 2 on its own, we just put an x on it, so it becomes 2. Oh, we're working. I've got to be careful here. Even in my head, I've just sort of swapped it straight away to an x, but we're working in v's, so this will become 2v. And then you've got the negative is there. This v to the minus 2, add 1 to the power, divide by my new power, so it becomes v to the minus 1 divided by minus 1, and then I just remember to add a constant of integration on there, c. And then simplifying this, the 2v doesn't need simplifying. The minus 1, if I put it to the front and multiply there with the minus that's there, minus minus is a plus, so you get plus, and v to the minus 1 is 1 over v plus c. Finally, part D. Finally, sorry, my computer went black there and to stand by, and I was worried it might stop the recording, so I've not got too much more to do. Just one more example, and then at least you can have a go. For part D, we're integrating x bracket 3 over x cubed plus 5 root x close brackets dx. So we're back to x's. Now here we have to multiply out your bracket first. So it's going to be, and in fact, that root x, I'm just going to write that as x to the power a half, because we can use rules of indices easier when they're numbers. Let's multiply them out. So I'm going to do x times this 3 over x cubed. Don't forget, if I multiply a fraction by something, I just put it on the top. So that becomes 3x. So it becomes the integral of 3x over x cubed. It just goes on the top. And then here, I need to do the x times the 5x to the half. So if I multiply this out, x times x to the half, we add the powers. Power 1, power a half becomes 3 over 2. And we get 5x to the 3 over 2 dx. Almost ready to integrate, and hopefully I've just got enough room on the bottom so you can see it. It becomes the integral of, well, one of the x's cancels with 1 there, so we get 3 over x squared, but the x squared needs to come to the top, so we get 3x to the minus 2, and then we've got the plus 5x to the 3 over 2 dx. And I'm now ready to integrate. We go term by term. Add 1 to the power, divide by my new power. So I don't need the dx and the integration sign now that I'm actually doing the integration. So if I add 1 to the power, it becomes minus 1, and I divide by minus 1. So it's 3x minus 1 divided by minus 1. Add 1 to the power, 3 over 2, add 1, or add 2 over 2. You get 5 over 2. So you get plus 5x to the 5 over 2 divided by 5 over 2, and then we just add c. Finally, we simplify. So the minus here just comes in the front, so it's minus 3x to the minus 1, or minus 3 over x if I take that down. And then this term here, instead of dividing by 5 over 2, we multiply by 2 over 5. So 2 times 5 is 10 divided by 5. That gives me 2, so we have 2x, and then the power is 5 over 2, and there's that plus c. Now there's a lot going on there, so what you might want to do, because I'm not going to deliver any more material at this stage, I'm going to try and do it in small bursts. I've been looking down now, the video is about half an hour long, 35 minutes. But the joy of this is I'm going to upload it when I set the assignment. So what I'll do is I will upload the notes for you shortly into Microsoft Teams. Once I've uploaded that, there'll be 2 exercises that you can do now on the back of this. In the book, so just let me grab the book, guys. In the book, obviously integration is chapter 13, so you should now be able to do, or have a look at, 13a and 13b. So you've got plenty to be getting on with over the next couple of days, and then I will upload another video next week which will just concentrate on 13c. This one has had a lot to talk about because you're just getting used to the process. But if you look on page, let me write these down, it's pages 288 to 293. If you look in there are a number of examples that you can have a look at just doing that process that I've been talking about. And you should be able to have a go at it. There is a notation, I will mention this before we finish, there is a little bit of notation that says that it can't be done for x to the power minus 1. So for example, I cannot integrate x to the minus 1 dx. We'll look at that more specifically later. Most of the examples you'll be fine. But the reason we can't integrate x to the minus 1 is because if I add 1 to the power, I get x to the 0, and I have to divide by my new power. Remember the process, add 1 to the power, divide by a new power. I would be dividing by 0, and that's undefined. Remember, we get math error. So we just have to be careful. That's one case, we just have to be careful. But we'll look in that in more detail. For the most part, just take this away. Integration is the reverse process of differentiation. It undoes what differentiation does. You either start with dy by dx or f dash x equals. Most of these with different letters you won't really see. In the book, they're all x's. But this is just a notation. It might, instead of saying dy by dx equals integrate this, or f dash x equals integrate, it might not tell you to integrate, and it gives it you like this, where you've got your integral sine dt, and you know that I'm integrating, and it's the t's I'm integrating, or integral sine, this is what you'll get in the book. This elongated s tells me I'm integrating these 2 terms, dx, and you know you have to go through the process, add 1 to the power, divide by a new power. So have a look at these, and it's exercise 13a and 13b that you can now do. During this video, I will upload it onto Teams, this is what I'm saying, and it'll be, as you go into Teams, you'll be able to, on the assignment, you'll be able to get the notes for this. So you'll be able to, if you can print it off, you'll be able to fill these examples in, because they're on the board there, you'll be able to watch the video and fill it in. If you can't, then just watch the video, but you might be, for example, the first bit, before I did these second lot of examples, the first section you just follow that, you just watch that little bit, and then have a go at 13a, read the examples over these pages first, check you understand it, and then have a go. Because you can obviously keep going backwards and forwards, pause it, look at the video as many times as you need to, and it's specific learning now for the books. But in addition, sorry, I was quite good at doing this, and then I've kind of lost my train of thought, but I've got it there. The video, I can't put it on the assignment. So when you go into Teams, on the assignment, it will have the notes. The other thing that you need to do, and I'll put a few notes on there, is to do the exercises 13a, 13b, check you can do it. The video, this video, it will be, if you go to the top of Teams, there's a file there, there's a link there for files, and if you go into that, then there'll be a folder called class materials, and I will store all the videos in there because there's no restrictions on size, etc. So going forward, I'll have a video, the date, and what it's to do with, so I'll try and be as descriptive as possible. But every time you want a video, you just go into files at the top, you just click on it, and there's a folder called class materials, which we can share out. You just click into there, and the videos will be there for you, and you can go back and look at them as many times as you want, and laugh at me doing my little bit on video. Hopefully this was useful. Do tell me how I can make this better. Let me know in the comments. Let me know any thoughts. I want to try and get this as right as possible. We've got potentially a few months that we need to be working like this, working together, but I'll be here to do videos when you would normally have your lessons, so that way you can try and, if not get your daily dose of me, at very least you can still be making progress at home. Right, thanks very much. I'll speak to you soon, guys.